Light feels permanent only from inside a brief chapter. Not dimmer than now, not quieter in the casual sense, not like a cloudy night or a galaxy seen through dust, a deeper change than that. An age in which light itself, the ordinary kind that pours from stars and scatters across gas and dust and makes structure visible, belongs to the past. The bright universe feels ancient from inside the present, yet the present is exactly where the bright universe lives. It is not the default condition of reality. It is a phase. Look up now, and the idea sounds wrong. The sky appears settled into abundance. Stars burn. Galaxies bloom. Nebulae glow. Even the darkness feels decorated. Everywhere the eye lands, something has been lit. The natural impression is permanence. Light seems woven into the basic design. But the universe does not promise to keep speaking that way.
But if that is only temporary, then where is the boundary where a luminous universe becomes a dark one? That question sits farther out than almost any human instinct can follow. It asks not when a particular star dies, not when a galaxy fades, not even when the last ordinary night sky disappears from some lonely world. It asks where one cosmic state becomes another. It asks what the final luminous regime looks like from the inside. It asks what survives when the conditions that once made the heavens bright can no longer be sustained. And the answer is stranger than a single ending. The universe does not go dark all at once. It sheds kinds of light one by one. First, the familiar brilliance thins, then the sources change, then the meaning of last light changes with them. The last star is not the last glow. The last visible sky is not the last energy release. The final bright object is not necessarily the final electromagnetic whisper.
What seems like one horizon turns out to be several, layered across stretches of time so vast that even the age of stars begins to look brief. For anyone drawn to thresholds like this, to the places where the universe stops behaving in familiar ways, subscribe and stay near the edge. Some ideas only become visible when taken all the way to their limit. Light feels permanent for a simple reason. Every scale of ordinary experience says that it is. Human history fits inside a blink of astronomical time. Civilizations rise and vanish, while the stars above them scarcely change. A lifetime is too short to catch stellar evolution in motion. Even written history has unfolded beneath essentially the same bright galaxy. The sky has had enough continuity to feel foundational. The sun strengthens that illusion. It is steady on the timescales that shape weather, oceans, and memory. Its light arrives each morning with such reliability that the mind stops classifying it as an event. It becomes background. That same habit expands outward. If one star can seem endless, millions of them can seem like a fixed condition. Add the Milky Way, add the galaxies beyond it, add the pale wash of ancient radiation left over from the early universe, and brightness starts to look less like an episode and more like a law. Yet stars are not eternal objects. They are thermodynamic arrangements. They exist by spending stored potential. A star shines only while gravity and pressure maintain the conditions for fusion, and fusion only works while usable fuel remains, and the core can still access the right temperatures and densities. Starlight is not a permanent substance. It is a process with a budget. That is true of entire galaxies as well. Galaxies do not manufacture light from nothing. They convert reservoirs of gas into stars, and stars into radiation, heavy elements, remnants, winds, and ash. The galaxy glows while those conversions continue. Once the fuel supply is locked away, blown out, swallowed, or exhausted, brightness declines. The system can remain gravitationally assembled long after its luminous youth has passed. That distinction endures. Structure can survive long after radiance fades. The universe's future is not mainly about disappearance. It is about transition. The objects remain, but the state of the cosmos changes. A bright, actively burning universe gives way to a remnant universe, then to an even thinner one. At the largest scale, the timing of this bright era is already a clue. The universe is about 13.8 billion years old, and stars have not existed for all of that time. For hundreds of millions of years after the hot beginning, there were no stars at all.
The cosmos had to cool, matter had to clump, the first gravitational wells had to deepen, and only then did the first stars ignite. Light from stars entered an already old universe. That alone breaks the illusion of permanence. If there was a time before starlight, there can be a time after it. And in fact, the era of peak stellar formation is already behind. The cosmos once made stars more vigorously than it does now. Galaxies in the distant past formed them at higher rates. Gas was more abundant. Interactions were more calming. Conditions were more fertile. The present universe is still bright, but it is living on the descending side of a great luminous arc. The stellar age is ongoing, yet it is no longer at its summit. The sky gives no hint of that. It still looks busy. It still overflows with sources. But abundance can conceal direction. A forest can remain green while growth slows.
A city can blaze at night while its power reserves quietly dwindle. A universe can appear rich in light while moving patiently and irreversibly toward less of it. The sun will not be the one to show the end. It is too large and too short-lived for that role. In roughly 5 billion years, it will exhaust the hydrogen in its core, swell into a red giant, reshape the inner solar system, cast off outer layers, and leave behind a white dwarf. The transition will be catastrophic for nearby worlds, but cosmologically, it is ordinary. This has happened to countless stars before, and will happen to countless others after. The death of a sun-like star does not dim the universe, it only reminds reality that stars are mortal. Larger stars burn even faster. Their brilliance is bought with extravagance. They fuse fuel at tremendous rates, live briefly, and die violently. Blue giants and supergiants are cosmic spendthrifts. They flood their surroundings with radiation, and then collapse, explode, or leave behind neutron stars or black holes after a few million to tens of millions of years. Spectacular light, yes. Long-term endurance, no. The real masters of duration are the small stars. Red dwarfs are easy to overlook precisely because they are so modest. They are faint, cool compared with the sun, and individually unimpressive from a human visual perspective. But the universe built them in enormous numbers, and physics favors their longevity. A low-mass red dwarf burns hydrogen slowly, mixes its interior efficiently, and can use a greater fraction of its fuel over time. Some of the smallest true stars may live for trillions of years. Not millions, not billions, trillions. That changes the emotional shape of the future. When the sun is long dead, when bright stars have cycled through their violent lives,
When many galaxies have already altered beyond recognition, red dwarfs can still be shining.
They extend the stellar age far beyond the lifespan of stars like the Sun. The last ordinary starlight is expected to come from these small, patient furnaces. But even that is not the whole picture. The universe has more than one way to keep a region luminous. Stars can form from gas. They can also emerge, in rarer cases, from mergers or collisions involving leftover objects. Brown dwarfs may combine and cross the threshold into hydrogen burning. White dwarfs in binaries can accrete material and flare or explode. Neutron stars can collide. Black holes can feed. Long after the easy fuel is gone, rare dynamical encounters can still create brief episodes of release. So the question starts to split. Is the last light the final light from a normal star that formed from ordinary gas? Is it the final light from any object still doing stellar fusion, even if that star was created late by merger? Is it the final visible glow an observer in some surviving system could witness with familiar senses? Or is it the final electromagnetic output of any kind, no matter how cold, faint, redshifted, or exotic? These are not evasions. They are what the far future forces. Near the beginning of cosmic history, categories line up neatly enough that star, light, and visible sky all feel closely related. Far enough into the future, they peel apart. To understand that separation, the universe has to be seen at the scale it actually occupies. A human lifetime lasts decades. Human institutions stretch at most through centuries. Recorded history covers a few thousand years. Measured against a planet, those spans already collapse into thin scratches. Mountains rise and erode across millions of years. Continents drift over tens to hundreds of millions. Mass extinctions punctuate geological time like hard commas. A world can preserve seas, atmospheres, and scars longer than any culture can imagine. Stellar time dwarfs even that. The Sun's main lifespan, about 10 billion years. A star large enough to explode can cross its full existence in a few million. A small red dwarf can continue burning for perhaps 10 trillion years or more. Place human history beside that scale, and it vanishes. Place the age of complex life on Earth beside it, and it becomes narrow. Place the full age of the current universe beside the lifespan of the tiniest red dwarfs, and even 13.8 billion years starts to look early. Then shift outward again. Galactic time is slower and more architectural. Stars orbit the Milky Way over hundreds of millions of years. Spiral structure changes, clusters disperse, encounters rearrange stellar populations. Over billions of years, galaxies merge, halos overlap, central black holes sink inward and coalesce. The Milky Way and Andromeda are expected to merge several billion years from now, reshaping the local group into a larger, more diffuse descendant.
To a civilization, that sounds like the end of an epoch. To cosmology, it is still near the front edge of the luminous era. And then comes the scale shift that ordinary intuition almost refuses. Take all of recorded human history and compress it into a spark. Take the age of agriculture, cities, mathematics, engines, telescopes, radios, rockets, and digital memory, and press it into something thinner than dust. Set that beside the Sun's lifespan, and it is negligible. Set the Sun's lifespan beside the lifespan of the faintest red dwarfs, and it shrinks in turn. Set the era of stars beside the full future allowed by black holes and quantum processes, and even the age of stars becomes a bright early interval. At cosmological depth, familiar time does not merely look small. It changes category. It stops being useful as a unit of feeling.
The bright universe exists in that context. Not at the beginning of everything. Not at the end of everything.
In the middle of a longer thermodynamic descent, the present sky feels spacious, but it is local to an era. That realization shifts the question from drama to geometry. The final light is not simply a last candle going out in a familiar room. It belongs to a room whose walls are moving, whose contents are aging at different rates, and whose future contains states with no human analog. To ask what the last light will be is to ask how reality behaves when nearly every common route to brightness has been cut off. Before getting there, one more illusion has to be broken. Light does not even remain equally available to observers while stars still exist. Cosmic expansion, especially under the influence of dark energy, pushes distant galaxies away from one another at accelerating large-scale rates. This does not tear apart bound systems like galaxies or local groups of galaxies, but it does widen the gulf between unbound regions of the universe. Over immensely long timescales, distant galaxies slip beyond observational reach. Their light becomes so redshifted, so stretched and diluted, that no future observer in the far local group descendant would see the wider cosmic web the way it is visible today. This means there are at least two different kinds of fading already underway. One is local production, how much fresh light the universe continues to make. The other is observational access, how much of the universe remains visible from any given place. A future astronomer, living trillions of years from now in the merged remnant of the Milky Way and Andromeda, may inhabit a region that still contains stars, yet see an outward sky emptied of external galaxies. The cosmos beyond the local island will not have ceased to exist. It will have slipped beyond practical view. In that sense, the visible universe ends in stages too. There is another kind of fading that belongs in this question, and it does not begin with stars dying.
It begins with distance itself becoming unusable. A universe can still contain light and still become less visible. That sounds contradictory at first, but it is one of the most important parts of the far future. The present sky does not only shine because stars exist, it also shines because the universe is still young enough, dense enough in visible structure, and dynamically open enough that light from remote places can still reach other remote places in meaningful ways. The wider cosmos is available. Distant galaxies are not just there, they are still connected to observation. That will not always be true. Dark energy changes the long-term geometry of visibility. On large scales, the expansion of the universe accelerates. Bound systems remain bound. Galaxies do not get torn apart internally by this expansion. The Milky Way stays together. Andromeda stays together until it merges with the Milky Way. The local group remains, in its own gravitationally tied way, a coherent structure.
But the larger universe beyond such bound islands keeps receding, and over time, that recession becomes harder to ignore. The consequence is not that other galaxies vanish in the theatrical sense. It is subtler and more absolute than that. Their light grows increasingly redshifted, increasingly delayed, increasingly diluted. Over vast intervals, galaxies not gravitationally bound to the local region slip beyond the practical horizon of observation, not beyond existence, beyond access. There will come an era when a future observer, if any remain, may look outward and see no evidence of the great galactic web that is obvious today. No clusters spread across a structured cosmic background, no long census of galaxies at immense range, no visible testimony that the universe once appeared crowded on the largest scales. The loss is scientific as much as visual. Present-day cosmology depends on a lucky position in time. The cosmic microwave background is still detectable. Distant galaxies are still visible.
Expansion can still be measured against rich, large-scale structure. The chemical record of stellar generations is still present in abundance. The sky still contains history in readable form. In the far future, much of that evidence fades from reach. The microwave background stretches to wavelengths so large and energy so low that it becomes increasingly difficult to detect. External galaxies pass beyond useful visibility. The local bound remnant of the Milky Way and Andromeda, with perhaps a few companions, may come to look like all there is. Not all that exists, all that can be inferred. That creates one of the strangest thresholds in the whole future of the universe, a time when the cosmos still has a past, but observers may no longer be able to reconstruct it from the sky. That distinction shapes this question, since the last light the universe will ever see is not only about what continues to shine, it is also about what light can still reveal.
The universe becomes observationally poorer before it becomes physically dark. The universe loses not only light, but context. That is a boundary in its own right. Imagine astronomy in such an age. The local galaxy remnant still contains stars for a long time. There may still be planetary systems, white dwarfs, brown dwarfs, neutron stars, black holes, and long-lived red dwarfs quietly burning in the darkness. But the greater universe has withdrawn behind the expansion. The visible sky has collapsed inward. What is left is a local island surrounded by a blackness that no longer opens onto obvious external structure. This would not merely change the appearance of the heavens. It would change the meaning of explanation. A civilization born late enough might infer a static island universe rather than an expanding cosmos born hot. It might see no direct evidence for the Big Bang, no visible field of distant galaxies running away, no bright relic background in any convenient form.
The largest truths known in the current age depend in part on living early enough to catch the evidence before the universe stretches it out of reach. So even before the final stars die, the universe is already moving toward a condition in which light tells less of the whole. That gives the whole question a second edge. The last light is not only about the final emission, it is also about the final age in which light still reveals the universe honestly. There is something almost cruel in that. The farther time goes, the harder it becomes for observers inside the universe to know what kind of universe they are in. The sky narrows, the evidence thins, the visible region becomes less representative of reality as a whole. The universe does not merely dim, it withholds context, and yet that same process sharpens the meaning of what remains. When a late red dwarf continues to shine in a sky that has already lost the wider cosmos, that star is not just a light source, it is one of the last local witnesses of a brighter regime. When a future remnant flares in a dark-bound system cut off from the visible web, the event stands out against a more profound isolation than anything imaginable now. The present sky makes brightness feel ordinary, partly because it is distributed. Light is everywhere. The far future makes brightness feel dramatic, partly because it is lonely. That loneliness begins long before the last light. It begins when the universe starts becoming too large to show itself. First, the cosmos loses distance. Then it loses abundance. Then it loses the easy machinery of starlight. That staging is important. since the phrase "the last light the universe will ever see" can mean the last light visible to some observer, the last light produced inside a bound region, or the last light generated anywhere.
The farther ahead the gaze moves, the more those become separate questions. Still, there is a natural place to begin: the long fading of ordinary stars. Star formation does not stop on a single date. Galaxies consume gas unevenly, becomes locked into stars, heated, expelled, stripped, or otherwise rendered less available for new stellar birth. The cosmic nursery empties. As that happens, the average stellar population ages. Short-lived blue stars disappear unless new ones form. Galaxies redden. Bright young clusters become less common. The spectrum of the universe changes with its demographics. A galaxy dominated by youth looks different from one dominated by long-lived survivors. The future sky is not merely fainter, it is older in composition. Eventually, truly ordinary star formation winds down. The age of easy ignition passes. The universe enters a phase where the stars that remain are mostly those already born, plus rarer latecomers produced by leftover interactions. This is still a stellar universe, but no longer a fertile one. It lives on inheritance. Among those inheritances, red dwarfs dominate the late luminous landscape. They outlast their brighter cousins by absurd margins. Some have not even had enough time yet in the current age of the universe to leave the main sequence. The cosmos is still too young for the smallest red dwarfs to have completed a normal stellar life. They were built for a future nobody has seen. Imagine the sky around one of them in the deep far age. Not the present Milky Way, crowded with populations at every stage. Not a rich cosmic web alive with countless visible galaxies. A thinner environment, a remnant galactic system, long merged and dynamically relaxed, containing old stars, white dwarfs, neutron stars, black holes, brown dwarfs, and among them, tiny, steady stars, still quietly burning. They would not blaze like young blue suns. They would persist. In a universe increasingly defined by what has ended, they would represent what still endures. That is why some candidates for the last ordinary light are expected to be red dwarfs or objects like them. They keep the old category alive longer than anything else. As long as a red dwarf shines through hydrogen fusion, the stellar era has not truly closed. The end of the luminous universe is often imagined only from the outside, as though the main question were how the sky looks from nowhere in particular. But light acts locally before it defines any grand view. It reaches surfaces, atmospheres, chemistry, and the possibility of warm environments. It shapes whether there can still be places where energy arrives in a steady enough form to sustain long-lived processes. That is where the deep future becomes unexpectedly intimate. A star is not just something visible, it is a source of order. Around it, temperatures can remain far from equilibrium, molecules can circulate, weather can persist, complex chemistry can continue. On at least one world known today, a star permits oceans, clouds, seasons, biospheres, memory, and observers capable of asking how long the age of stars will last. So another way to understand the last light is to ask a related question. Where are the final refuges of persistent warmth? In the present universe, the answer is common. Nearly every galaxy contains stars. Many stars may host planets. Energy gradients are abundant. But the deeper the future goes, the more those refuges concentrate around the longest-lived stars and the rare systems that can still channel stored energy in useful ways.
This is why red dwarfs matter so much, not only as the final ordinary stars, but as the final steady worlds of heat. A small red dwarf burns slowly enough to stretch stellar life into the trillions of years. That does not guarantee friendly planetary conditions. Red dwarfs can flare violently, especially in youth. Their habitable zones lie close in, which raises issues of tidal locking, radiation exposure, atmospheric erosion, and magnetic protection. But in the very long run, once the more massive, shorter-lived stars have disappeared, red dwarfs become the principal remaining sites where steady starlight still exists at all. That changes the geography of possibility. The future of ordinary warmth belongs less to sun-like systems and more to dim, close, stubborn stars. If any worlds remain geologically or atmospherically viable around such stars, they could outlast Earth's kind of habitability by colossal factors.
A universe already old beyond ordinary imagination may still contain pockets where light falls predictably on a surface, where temperatures hold in stable bands, where chemistry proceeds under a continuing sun. That does not make the far future welcoming, it makes it structured. These last islands of warmth would exist inside a universe that has otherwise thinned dramatically. The external sky would grow darker and poorer. The stellar population around them would age. Nearby bright stars would be scarce. But locally, around the smallest long-lived suns, energy could still arrive day after day in a way that belongs unmistakably to the old stellar order. This shapes the emotional architecture of the piece. The end of the luminous universe is not only a matter of losing spectacle, it is the loss of regions where sustained gradients are easy. It is the loss of environments where light does not merely appear, but governs daily physical life. That loss happens in layers too.
First, the most massive stars disappear, taking with them short, brilliant eras and violent blue light. Then stars like the Sun are gone, closing the chapter of mid-range, stable systems familiar to present intuition. After that, the last red dwarfs continue almost alone, making the final long-lived stellar habitats possible. And then even those are over. Once the last fusion stars have faded, warmth becomes more difficult to arrange. There may still be isolated sources, tidal heating in old gravitational systems, accretion around compact remnants, radioactive decay in interiors, residual cooling from white dwarfs or neutron stars, perhaps even artificially maintained environments, if intelligence and engineering survive anywhere far enough into deep time. But the broad, easy situation of worlds warmed by stars has ended. The universe after that is not empty of energy. It is empty of accessible, ordinary, renewable stellar warmth. That is a much harsher threshold than the phrase, "the last star dies," first suggests.
The death of a star is an astronomical fact. The end of steady warmth is a civilizational and thermodynamical fact. The future beyond starlight is not merely darker overhead, it is harder to inhabit. Even white dwarfs, for a time, complicate the boundary. A newly formed white dwarf begins hot and cools gradually. For an interval, a close orbiting world could, in principle, receive substantial radiation. But this is not the same as the long, stable main sequence life of a star. The habitable geometry is narrower, the evolution harsher, the long-term trend relentlessly downward. A white dwarf can preserve a last echo of stellar warmth, but not the full logic of the stellar age. Brown dwarfs, too, emit residual heat, especially when young, but they never ignite sustained hydrogen fusion. They are bridges between planets and stars,
and in the deep future, they populate a universe of dim, cooling leftovers. Yet they do not restore the luminous order either.
They occupy the borderland between light as source and light as after effect. And that is the pattern the whole cosmos is following, from active production to stored residue, from stable output to gradual cooling, from common energy gradients to rare and special ones. The last islands of warmth are therefore also the last places where the old universe still behaves like itself. A red dwarf shining on a close rocky world in the far future would not just be a late star, it would be a surviving piece of the cosmic Middle Age carried almost impossibly forward. Around it, there could still be mornings, there could still be shadows, there could still be a sky made meaningful by a local sun, even as the wider universe had already become much darker and much lonelier. That local continuity makes the end more powerful, not less. It means the stellar universe does not vanish only at the scale of galaxies, it vanishes at the scale of lived conditions. The last light is also the last dependable arrival of warmth on a world. After that, any surviving structure must depend on colder, narrower, rarer channels of energy. Accretion events, tidal leftovers, slow gravitational settling, collision-driven bursts, artificial systems, if any exist. Not a sky that naturally shines for trillions of years over stable surfaces. The phrase, "what survives when conditions become impossible," belongs here as much as anywhere. Some worlds may survive as objects. Remnants certainly survive. Matter, if stable, survives. Orbits survive for a time. But the condition of being in ordinary star-fed environments becomes impossible once the last red dwarfs go dark. What survives after that is not the old way of living under a sky. It is the remnant condition. That is another reason the final ordinary light is so important. It is the last light that still belongs to a universe where warmth can be persistent and natural, rather than accidental and brief.
When it disappears, the cosmos becomes something colder in more than one sense. But even red dwarfs do not last forever. When their fuel finally runs out, the universe loses its most conservative luminous engines. There is debate in the details of how the smallest stars evolve at such late times, and no observation can directly confirm a full life cycle on those scales yet. But the broad expectation is clear. The stars fade into remnants. White dwarfs cool. Neutron stars cool. Brown dwarfs remain substellar and dark. The sky enters an age of leftovers. This is where language can mislead. The end of the stars sounds like a sudden event. In reality, it is better imagined as a coast that stretches across immense time. At one end, bright stars are common and star formation continues. Farther along, new stars are rare and old low-mass stars dominate. Farther still, only the last long-lived stars remain. After that, stellar fusion as a familiar cosmic industry effectively ceases. Yet even then, the universe is not fully dark. Dead stars are not instantly invisible. White dwarfs begin hot and cool slowly. Intuitive candidate for the last ordinary light, then, is the final star still shining by fusion. Not the last bright star, not the last star visible from Earth, not even necessarily the last star ever born in a conventional sense. The last surviving star-like object still generating familiar starlight from fusion. That object or class of objects is likely small, dim, and long-lived. Its importance comes not from spectacle, but from position. It would mark the closing edge of the stellar era.
While it lives, the universe still contains what the present mind most readily recognizes as a star. But if the question is pushed harder, that answer starts to feel incomplete. Suppose the last red dwarf has finally faded. Has the universe seen its last light? No, it has seen the end of ordinary starlight, not the end of luminosity itself. That distinction opens the next regime. After the stellar era, cosmologists often speak of a degenerate era. The name sounds severe, but it refers to a specific physical condition. Much of the remaining visible structure is built from degenerate remnants: white dwarfs supported by electron degeneracy pressure, neutron stars supported by neutron degeneracy and nuclear forces, and black holes defined by collapse beyond those supports. Brown dwarfs and cold planetary bodies also persist, but the long-term inventory becomes increasingly remnant-heavy. The universe turns from active burning to stored residue.
It is a different cosmos. Instead of abundant stars steadily converting hydrogen into light, there are cold embers, compact corpses, and dark companions moving through a vast, slowly changing gravitational architecture. Processes continue, but they are sparse and contingent. Energy release no longer comes from the common rhythm of stellar interiors. It comes from encounters, decays, accretion, mergers, and perhaps quantum events so rare that occasional becomes a meaningless word. This is one of the major boundaries in the future of the universe, and it changes almost everything. Before it, the default luminous object is a star. Before it, the night sky is filled by ongoing fuel consumption inside hot plasma. Beyond it, any glow has to be earned by special circumstances. That is why the boundary is so important. It is not just a dimming, it is a change of regime. In a stellar universe, darkness is what lies between sources. In a remnant universe, light is what interrupts darkness.
By the time this transition is far advanced, galaxies as present observers know them will already have transformed. Stellar populations will have aged and mixed. Ordinary planetary systems will have experienced eons of orbital evolution, perturbation, stripping, and cooling. Encounters between objects, though still uncommon in absolute terms, accumulate across immense spans. Some remnants are ejected, some sink inward, some pair up. The universe becomes less like a living city and more like the ruins of one, where only rare sparks betray continuing activity.
That is why the end of the stars can be misleading. It sounds as though galaxies simply run out of bulbs. In reality, galaxies change character step by step until their brightness is no longer the expression of an active stellar ecosystem, but the residue of what used to be one. A future galaxy remnant is less like a city going dark and more like a city turning into ruins while a handful of windows remain lit. Consider the likely future of the Milky Way and Andromeda. Over the next several billion years, they are expected to merge, along with the broader evolution of the local group. The result is often imagined as a single, larger elliptical-like remnant, sometimes informally called Milkomeda, though the exact structure depends on many details of the merger and the later dynamical history. What matters here is not the label, it is the transition. Two spiral galaxies with active stellar populations and ongoing internal structure become a larger, older, more mixed, and dynamically relaxed descendant. That merged remnant will still contain stars. For a very long time, it will still contain many stars, but its future is already pointed toward aging.
Star formation in such a system depends on available gas. Mergers can trigger bursts of star formation by compressing gas, but they also accelerate its use. Energetic feedback from stars and central black holes can heat or expel gas. Over enough time, the cold, raw material needed to make new stars grows scarcer. The galaxy becomes less a nursery and more a census of survivors. Its light changes accordingly. The brilliant, short-lived stars that once marked youthful regions vanish unless new ones keep forming. Color shifts, population ages, compact remnants accumulate. The bright arms and contrasting stellar neighborhoods familiar in younger galaxies give way to older, smoother distributions. Then comes the deeper transformation.
Over immense intervals, even the internal architecture of a galaxy continues to loosen. Gravitational encounters, though weak individually, add up. Orbits change. Objects are scattered. Some stars and remnants are ejected into intergalactic darkness. Others sink towards the center through dynamical processes. Binary systems harden or break apart. Dense environments promote rare collisions. Black holes may merge. The galaxy is no longer organizing itself around birth. It is reorganizing itself around leftovers. This is when a galaxy starts to resemble a graveyard, not in the melodramatic sense of total stillness. Graveyards still have arrangement, memory, and occasional movement. But the dominant population is no longer the living architecture of stellar birth and midlife. It is remnants. White dwarfs become common markers of once normal stars. Neutron stars and black holes carry the collapsed history of more massive ones. Brown dwarfs drift among them. Objects that never became full stars at all. Cold planets, rogue or bound, survive in darkness.
Debris belts persist until ground down, scattered, or swallowed. The galaxy remains populated, but the population is post-luminous in character. The last light does not emerge from empty space, it emerges from these graveyard systems. A late flare in the far future would happen inside an environment loaded with history, but poor in renewal. A white dwarf accreting from a surviving companion is not merely an isolated binary, it is one of the few remaining channels through which a dead stellar population can still briefly mimic the violence of youth. A neutron-star merger is not just an energetic event, it is a graveyard collision, a release from the compressed remains of stars that died ages before. A black hole feeding on a remnant is a dark object extracting one last bright interval from what the galaxy has left. In a young galaxy, events like these are part of a crowded field. In an old graveyard galaxy, they stand almost alone. The difference is dramatic.
Imagine a future epoch in which the main sequence is nearly deserted. No large blue populations, no ongoing widespread star formation, no richly structured glowing arms, just the dim, persistent output of low-mass stars, if any remain, plus the faint cooling of countless remnants. Then, after an interval so long that ordinary chronology loses emotional force, a compact binary spirals inward and detonates, or merges. For a brief time, the ancient graveyard speaks in light. Then it falls silent again. That rhythm may define much of the late luminous universe, long, tomb-like quiet, interrupted by bursts from the dead. The graveyard picture also clarifies why the last light cannot be understood only as a function of fuel. Dynamics matter too. Even a mostly exhausted galaxy still contains motion, and motion over enough time becomes opportunity. Close encounters that are fantastically rare on short timescales become almost inevitable somewhere on long ones. Orbits cross, companions exchange, ejections happen, captures happen.
Systems that seemed inert at one age become unstable at another. This is one reason the late universe remains interesting even after star formation is effectively over. The graveyard is not frozen, it is slowly processing itself, but it is processing itself toward lower and lower probabilities of brightness. Every late flare consumes one of the rare situations that can still produce one. Every merger reduces the pool of available compact binaries. Every accretion event drains a local reservoir. Every ejection removes an object from the dense environment most likely to generate encounters. The galaxy remains active in the broad mechanical sense, yet the conditions for visible release become harder to meet over time. So the graveyard grows quieter. Eventually, even its rare fireworks thin to near nothing. The galaxy still exists gravitationally for a very long time, but its visual identity is gone. It has become a structure defined less by what it emits than by what it contains. That is a profound state change.
Present-day galaxies are discovered and studied largely through light. Deep future galaxies, if the word still applies cleanly, may be better understood as dark-bound repositories of remnants. Their past remains encoded in composition, mass distribution, orbital traces, and compact objects, but their visible self-expression has mostly ended. A universe full of such graveyards is not yet the final dark era. It still has structure. It still has encounters. It still has black holes. It may still have a few tiny stars, but it has already crossed out of the galaxy age in the familiar sense. The places once known by their light are now known by their dead, and that is exactly the kind of environment from which the last meaningful flashes emerge, not from a thriving cosmos, from a cemetery that occasionally remembers how to burn. One of the easiest mistakes to make about the far future is to imagine it as gentle.
The temperatures fall, the stars fade, the sky empties, everything cools. All of that is true, and yet, the late universe is not defined by quiet alone. It is also shaped by stored violence released on increasingly rare terms. When ordinary stars dominate, energy comes from stable fusion inside hot plasma. The violence is present, but it is domesticated into steady output. A sun shines rather than explodes, at least for most of its life. Even massive stars, for all their instability, spend most of their time in an organized luminous state. The universe's violence is moderated by abundance and routine. When stars are gone, that moderation weakens. The remaining objects are smaller, denser, older, and often more dangerous per unit mass. White dwarfs pack stellar mass into planetary volume. Neutron stars compress still further. Black holes represent collapse taken beyond any surface that light can escape. These are not peaceful objects.
They are extreme states held together by pressure, quantum statistics, relativity, or the lack of any known support at all. Left alone, many of them simply cool or drift. But the far future is long enough that left alone cannot be assumed forever. Encounters happen. Binaries decay. Passing objects perturb old systems. Dense environments channel rare close approaches. Once these leftover objects interact, the results can be violent,
in ways a faded universe seems almost too old to produce. White dwarfs provide one route. If a white dwarf in a binary system accretes enough matter from a companion, its surface can ignite in runaway flashes, producing novae. Under more extreme circumstances, if its mass approaches a critical threshold, the star can undergo catastrophic thermonuclear disruption as a Type A supernova. In the present universe, such events are part of an active astrophysical landscape. In the deep future, they would become relic violence, bursts generated by stars that had already died ages before.
Neutron stars offer another route. Their mergers are among the most energetic known events, releasing gravitational waves, heavy elements, and electromagnetic counterparts under the right conditions. Such binaries can survive for immense intervals before inspiraling through gravitational radiation. In a late remnant universe, a neutron star merger would be a startling punctuation mark, an ancient compact pair finally cashing in an orbit that had been shrinking almost imperceptibly for ages. Black holes intensify the pattern. Matter falling toward a black hole can radiate with extraordinary efficiency before crossing the horizon. In the young universe, active black holes can blaze as quasars. In the far future, easily available gas is scarce, so such brilliance becomes rare. But rare is not the same as impossible. A disrupted star, a captured remnant, a dense disk assembled from leftovers, any of these can still produce a burst of light around an object otherwise associated with perfect darkness. There is something almost paradoxical here. As the universe becomes colder and more exhausted, the individual acts of release that remain can be more concentrated and more extreme. The average state is quieter, the exceptions are harsher. That is the slow violence of leftover matter. It is slow in preparation. It may take millions, billions, or vastly more years for the right configuration to emerge. A binary hardens by tiny increments. An orbit is nudged by repeated perturbations. A compact object drifts through a dense environment until a close interaction becomes unavoidable. Matter accumulates grain by grain, stream by stream. Gravitational waves siphon angular momentum with impossible patience. Then, when conditions align, release comes fast. This fits the larger theme of thresholds beautifully. The far future is full of boundaries that are crossed only after absurdly long waiting. And when those boundaries are crossed, reality can change state in an instant. A white dwarf crosses a mass threshold and detonates.
Two neutron stars cross the point of no return and merge. Matter around a black hole crosses an inner orbit and is converted into a last bright torrent. These are not ways of preserving the stellar age. They are ways in which a dead universe still finds channels to produce light. The question changes here. If the last ordinary light comes from the final stars, the last dramatic light may come from the compressed dead. The late universe is not governed by continuity. It is governed by thresholds inside leftovers. That also means the line between ordinary and extraordinary becomes sharper with time. In a young galaxy, a supernova is spectacular, but it happens in a universe full of other luminous things. In a graveyard galaxy, a comparable release would stand against an enormous silence. The same physical event becomes more isolated, more defining, simply because the background has changed. there is a deeper thermodynamic lesson here too.
The far future does not eliminate energy release all at once. It progressively removes the easy paths and leaves behind the steep ones. Broad reservoirs of usable gas are lost first. Common stellar burning follows. What remains are the trapped, compressed, or delayed channels, objects where energy is stored in gravity, degeneracy, orbit, or quantum instability, waiting for an unlikely trigger. That is why the late universe remains physically interesting long after it ceases to be visually rich. It is a place where almost all common routes to brightness are closed, and yet a few narrow paths remain open. Those paths are enough to produce the last episodes of non-trivial light. Even the word accident becomes too casual for this. These are not random fireworks. They are consequences deferred. A neutron star merger in the far future may be the endpoint of stellar evolution, binary formation, gravitational radiation, galactic scattering, and deep time persistence all at once.
A black hole flare may be the last chapter in the life of a system that began as an ordinary star when the universe was still crowded with galaxies. The late flash contains an old universe in it. That gives every final event a kind of compression. It is not just bright, it is historically dense. And because these events are so historically dense, they also help explain why the last light cannot be only one object or one moment. Different channels end at different times. The final steady light from stars ends on one timescale. The final violent release from remnants ends on another. The final evaporation from black holes ends later still. The future is sorted less by a single terminal event than by the closing of one energy pathway after another. By the time only the slow violence of leftover matter remains, the universe has already crossed far beyond its familiar condition. Yet it is not silent. Silence is still being approached.
The darkening universe does not stop speaking at once. It first loses its everyday voice. Then it speaks only in rare eruptions. Then even those fade. That is the late arc in its cleanest form. At this point, the scale has shifted enough that another question becomes unavoidable. What exactly counts as a boundary? There is a practical boundary for observers. A future civilization could live at a time when the sky no longer contains external galaxies, when nearby stars are scarce, when the cosmic microwave background has redshifted to wavelengths difficult to detect, when the universe appears locally static and islanded. For such observers, a luminous cosmos may seem much smaller than the one visible now. Their last light may arrive early. There is a boundary for ongoing star formation. When gas no longer readily collapses into new stars, one mechanism of cosmic renewal is over. There is a boundary for stellar survival. When the final fusion-burning objects are gone, ordinary starlight ends.
Then there is a boundary for remnant-driven luminosity, when the remaining flashes become dominated by increasingly exotic and increasingly infrequent processes. And beyond even that lies a deeper threshold still, where the main surviving engines are black holes, and the possibility of proton decay changes the inventory of matter itself. This is the point where far future cosmology stops feeling like extrapolated astronomy and starts feeling like a map of attrition. Consider proton decay. Protons, as far as observation currently shows, appear stable over extraordinarily long timescales. No confirmed proton decay has ever been seen. The Standard Model, in its simplest tested form, does not require it, but many grand unified ideas allow or expect it on absurdly long timescales. If protons do decay, ordinary matter is not permanent. The atoms that build planets, bodies, gas clouds, rocks, and cold remnants would not merely cool. They would slowly come apart. If proton decay occurs, the degenerate era becomes thinner. Much of what would otherwise remain as cold material eventually leaks away into leptons, photons, and other products, leaving black holes as the most durable large structures. If proton decay does not occur, matter can survive much longer in cold, degenerate forms, enabling even more remote processes, some of them fantastically speculative. Either way, the far future darkens. The difference is in how fast the inventory of normal matter is erased and what exotic leftovers are still available later on. This is one of the moments that calls for the most caution. There is no observed proton decay. Any statement about it belongs in the category of long timescale possibility, not established fact. But the very fact that the fate of matter may hinge on unknown physics reveals something profound about the question of the last light. The late universe is not determined solely by astronomy. It also depends on particle physics at energies and durations no experiment can directly span. Suppose protons do decay, then over stupendous durations, remnant objects made of baryonic matter would gradually disintegrate. White dwarfs would not remain intact forever. Planetary debris would erode not only through collisions and ejection, but through particle-level instability. Radiation products drift. Black holes, having swallowed matter or formed earlier from collapse, increasingly dominate the long-term mass budget of whatever remains bound. Suppose protons do not decay, then matter can persist in compact, cold remnants much longer, permitting an even slower and stranger future. Some models suggest black dwarfs could eventually undergo nuclear reactions or tunneling processes after imaginable spans, producing very late flashes, almost impossible-looking echoes of stellar explosions from objects that had long since frozen. These possibilities are deeply speculative, resting on physics extended far beyond any tested domain, but they matter conceptually.
They show that last light may depend not only on what survives, but on whether the dead can still be pushed into one final release. There is a point in the far future where the objects under discussion do not even exist yet, not because they are hypothetical in the sense of being invented, but because the universe is not old enough for them to have formed. Black dwarfs belong to that category. A white dwarf is the hot remnant left behind after a lower mass star sheds its outer layers. It begins bright by remnant standards and cools over time. Given enough time, far more than the current age of the universe, it should radiate away that stored heat and become a black dwarf, a cold, dark, inert stellar remnant. No black dwarfs should yet exist. The cosmos has not had enough time to make one. That single fact is enough to stretch the imagination.
The universe is old enough for galaxies to collide, stars to rise and die, heavy elements to accumulate, planets to form, life to emerge, and intelligence to wonder about the fate of everything. Yet it is still too young for a white dwarf to finish cooling all the way into darkness. Black dwarfs belong to a future beyond all recorded astrophysics. They are remnants of remnants. At first, they sound like the final end of a star's life, a cold, dead ember, silent forever. But the far future rarely permits such clean endings without qualification. Once again, the dead may not stay fully dead. In some speculative but physically motivated discussions, black dwarfs may still undergo rare nuclear events after unimaginable timescales. The reason is not that they remain hot enough for ordinary fusion. they do not.
The reason is that quantum tunneling and extremely slow pycnonuclear processes inside dense cold matter might, over enough time, allow heavier nuclei to fuse or rearrange in ways that eventually destabilize the object. Under certain assumptions, some black dwarfs could, after fantastically long intervals, explode in events sometimes described as black dwarf supernovae. This idea is far more speculative than ordinary stellar evolution. No such object has ever been seen. No black dwarf exists yet to observe. The timescales involved are so far beyond current empirical reach that the discussion is necessarily theoretical. Still, it is an important possibility for one reason. It shows that the universe may retain ways of producing light long after all familiar stars have disappeared, and even long after their remnants have gone cold. That is conceptually profound. A black dwarf, in intuitive terms, should represent the end of the line, a star that burned, died, cooled, and vanished into darkness.
If even such an object can, under the right conditions and after absurd delay, produce one last explosion, then the phrase "last light" becomes even more layered. The universe's dead are not only stored history, they may be future fuel in forms too slow and strange for ordinary language. This does not mean the dark future is secretly busy. It is not. Even if black dwarf explosions are real, they would be staggeringly rare and separated by lengths of time that make all earlier cosmic eras feel crowded. But rarity at this scale is not insignificance. A single such event in a universe otherwise almost entirely dark would carry enormous interpretive weight. It would be one of the few remaining ways the cosmos could still generate a recognizable flare from matter that had once seemed fully exhausted. It also sharpens the distinction between a last star and a last light. A black dwarf explosion, if possible, would not be ordinary starlight.
It would be a delayed release from an object that had long ago ceased to be a star in the active sense. Yet to any observer present, the event could look more dramatic than the quiet fading of the final red dwarf. The physically last meaningful light and the emotionally last familiar light need not coincide. There is something fitting in that. The universe begins with states so hot and dense that ordinary matter is not yet settled. It then enters long eras where stars shine steadily and structure flourishes. In the deep future, after cooling and thinning far beyond familiarity, some of the final fires may come not from hot young plasma, but from cold, dense corpses crossing rare thresholds after a nearly eternal wait. Fire returns, but only as exception. That is one of the clearest patterns in the whole far future. Common processes become rare. Rare processes become defining.
The universe does not keep its old kind of activity alive. It changes the conditions under which activity is still possible. Black dwarfs sit almost perfectly at that threshold. They are born from ordinary stars, yet belong to a future where ordinary starlight is over. They are cold, yet under some models they may still harbor roots to one final release. They are graveyard objects, but not necessarily the last word. Even if the black dwarf supernova picture turns out not to survive more complete physics, the larger lesson remains. The future contains regimes where tiny probabilities have enough time to accumulate into real events. When thinking about the final light, human intuition tends to undercount this. It imagines the universe as either active or dead. In truth, the universe spends immense time in intermediate conditions where activity is not impossible, only rare. That rarity reshapes meaning. In a bright galaxy, a supernova is one event among many.
In a cold remnant universe, a single flare can define an age. So black dwarfs, whether or not they truly explode in the end,
earn their place in the narrative. They force the question to remain open a little longer. They stop the piece from collapsing too early into a neat answer. They remind the viewer that the farther ahead reality is followed, the more careful one must be with the word final. There may be a last ordinary star. There may be a last hot remnant. There may be a last rare explosion from cold matter. And later still, there may be the last black hole evaporation. Each layer pushes the end outward. That is not padding. It is the architecture of the subject. The universe does not hold one ending in reserve. It stores many, nested inside one another, each revealed only after the previous source of light has become impossible. And black dwarfs sit exactly where the impossible begins to blur. In either case, the universe crosses a decisive threshold when ordinary starlight ends. That is the line between a cosmos where luminosity is common and one where it is rare. But it is not yet the line between light and none. Beyond this stage, what used to be called the night sky has become something far emptier. There may still be glows, there may still be bursts, there may still be radiation from cooling remnants, infall, collisions, annihilations, or decays. Yet the background assumption has flipped. The dark is no longer the canvas behind the bright universe. It is the main condition, interrupted only by rare events. What changes beyond that boundary? First, no new ordinary generations of shining stars refresh the cosmos in the way the present universe still can. The luminous population becomes terminal. Second, visibility becomes local and event-based. There is no richly populated sky of ongoing stellar communities stretching in every direction. There are isolated remnants, chance interactions, and occasionally a flare that would have seemed ordinary only in a much younger universe. The meaning of waiting changes. In the current age, millions of years can separate major astrophysical events in a given region and still feel like finite intervals inside a busy cosmos. In the remnant future, the intervals between luminous events can become so vast that between one flash and the next describes spans wider than the entire history of stars before them. Temperature and energy gradients flatten as well. Heat death is not a moment when everything reaches identical conditions instantly. It is the long erosion of usable differences. Light, as a concentrated release from ordered energy sources, becomes harder to produce once those gradients have been spent and the available paths to fuel have narrowed. What still shines often does so through violence rather than stability. The old universe glowed through persistence, billions of stars quietly maintaining fusion.
The late universe glows through accidents, mergers, captures, decays, evaporation. Brightness is no longer a settled condition. It becomes an event. That last change is especially important if the question is not merely, what is the final photon, but what is the last light in any meaningful sense? A single weak thermal photon emitted by a cooling object does not feel like the answer, even though physics permits endless low-level emission from many systems for long spans. The better interpretation is to look for the final significant luminous mechanisms, the last kinds of processes capable of producing identifiable episodes of release. That leads towards black holes. Black holes often seem like the ultimate darkness, and in a local sense they are. Light that crosses the event horizon does not return. Yet far future physics gives black holes a second identity. According to Hawking's theoretical result, black holes are not perfectly black when quantum fields are considered near the horizon.
They should radiate thermally, losing mass extremely slowly. The smaller the black hole, the hotter the radiation. Large black holes are colder and evaporate far more slowly. A stellar mass black hole would take something like 10 to the 67 years to evaporate. The supermassive black holes at galactic centers could survive for durations closer to 10 to the 100 years or more, depending on mass. Nothing observed has yet directly confirmed Hawking radiation from astrophysical black holes. The expected signal is far too faint relative to current cosmic backgrounds. But the idea rests on well-known theoretical ingredients and is treated seriously as one of the strongest predictions about the extreme late future, even if empirical confirmation remains out of reach for now. If Hawking radiation is correct, then black holes are not final storage. They are delayed release. The answer changes completely here. The last star may produce the last ordinary light.
The last visible familiar flare may come from a rare remnant collision or accretion event, but the final sustained energy release from major surviving objects may come from the evaporation of the last black holes. And if the question is asked in the broadest physical sense, what is the last light the universe will ever produce, then the best current answer points not to a star at all, but to the final Hawking radiation from the last evaporating black hole, unless unknown physics alters the ending. That answer sounds almost backward. The universe begins hot, forms stars, builds galaxies, fills itself with radiant structures, and ends not with a grand final sun, but with darkness slowly bleeding out of objects famous for swallowing light. The brightest age belongs to the middle. The last glow belongs to what once seemed least luminous. Yet even this answer needs care. A very large black hole radiates at an extremely low temperature. Much of its Hawking output would be in very long wavelengths at first, not a visible blaze. Only near the end of evaporation, as the black hole becomes lighter and hotter, would the radiation intensify dramatically. The final phase, in standard theoretical pictures, could involve a burst of high-energy emission. But by then, the universe around it is so altered, so empty, so cold, and so late, that calling it the last light risks importing present intuitions into a realm where familiar categories barely hold. Still, among all known candidates, the terminal evaporation of the last black hole is one of the most compelling endpoints for any non-trivial luminosity. Black holes can outlast stars, outlast most ordinary matter if proton decay occurs, and persist into an era where almost nothing else of macroscopic scale remains active. They effectively reserve a final release for the end of deep time. To feel what that means, it helps to walk the ladder again. In the current universe, light is common. In the far stellar future, light becomes older and redder. After the stars, light becomes rare and event-driven. After most remnant interactions have thinned, black holes dominate the long game. Then even black holes evaporate, and after that, if current ideas hold, the universe enters an even darker age still. This later state is often called the Dark Era. The phrase sounds dramatic, but it is really descriptive. It refers to a cosmos where no stars shine, no substantial black holes remain, and the contents are mostly very low-energy particles, dilute radiation, perhaps stable remnants if particle physics allows them, and a geometry still expanding under dark energy. The Dark Era is not an explosion's aftermath. It is thermodynamic exhaustion stretched across incomprehensible time. Here, the meaning of survival changes again. What survives when conditions become impossible for ordinary light? Not suns. Not galaxies in the way the present sees them. Not warm planetary surfaces, and not rich skies full of visible external structure. What survives are residues, particles, faint backgrounds, perhaps isolated bound relics if any remain, and the consequences of earlier events carried forward by expansion. Survival becomes less about objects continuing as recognizable actors and more about information being thinned into state. If proton decay happens, then much ordinary matter has already dissolved long before the last black holes evaporate. If it does not, cold remnants can linger in bizarre isolation even longer, but they do not restore the old luminous order. Either way, ordinary conditions for light have become impossible in the sense relevant to human imagination. There is no widespread fuel cycle, no active stellar ecology, no luminous architecture spanning the sky. The universe has crossed out of that mode.
That is the real state change at the heart of the question. The last light is not merely the end of brightness. It is the marker of a transition from one kind of universe to another. One can call the current cosmos a luminous universe, not just because it contains light, but because light organizes its visible identity. Galaxies are recognized by starlight, nebulae are seen in emission, heavy elements are traced through spectra, planets are found by reflected or blocked light. Astronomy in the present age is largely the reading of radiation from active structures. Even the oldest relic light, the cosmic microwave background, still speaks from a time when the universe was far hotter and denser than now. In the dark era, that relation collapses. Radiation no longer defines a rich visible order. What remains is too thin, too cold, too delayed, too stretched. The universe still exists, physics still exists, but the luminous face of the cosmos has ended.
There is an unsettling elegance in that. For most of cosmic history, if current understanding is right, the universe is either too early for stars or too late for stars. The Bright Age occupies a band between those extremes. It is vast by ordinary standards, but finite relative to the full thermodynamic descent. The era that produced observers who could ask about the last light sits inside that band. The question itself is a product of the luminous age. That makes the current sky look different. Every star overhead is not only a source, it is a sign of epoch. The Milky Way is not just a galaxy, it is evidence that the universe is still in its radiant interval. The sun is not merely a local energy supply, it is one example of a condition that will not persist forever. Even the quiet red dwarfs in the galaxy are future-bearing objects, small lanterns built for a later age.
The most extreme version of the question pushes beyond all of that and asks whether the very notion of a final light remains meaningful in an endlessly expanding universe. If time continues without bound, can there be a last anything, or only an asymptotic thinning where events become arbitrarily rare? This is where far future cosmology brushes against philosophy, though the physics still leads. A process can end even in an eternal time axis. Star formation can cease. Stellar fusion can cease. Black holes can evaporate. After the final example of a given event, there is indeed a last one, even if the universe continues afterward in a quieter state forever. Eternity after an ending does not undo the ending, it just makes the silence longer. But some caution remains. New physics could intervene. Vacuum decay, if it occurs, could rewrite the entire question by ending the present vacuum state catastrophically and replacing it with different laws or particles.
There is no evidence that such a transition is imminent, and it may never happen, but it is one of the speculative possibilities that sits in the background of far future reasoning. Dark energy itself may or may not be a true cosmological constant. If its nature differs from the simplest assumption, the long-term expansion history could change. Unknown particles, decays, or interactions could alter the late inventory of matter and radiation. These are not excuses to stop the inquiry. They are part of answering it responsibly. The farther the gaze goes, the more any confident ending depends on which pieces of fundamental physics remain stable. Still, across that uncertainty, some conclusions hold with unusual strength. Stars are finite. The era of ordinary starlight is finite. The visible richness of the present sky is not permanent. The universe will cross a boundary after which light is no longer its defining feature. That is enough to anchor the question, even before the deepest speculative layers are added.
There is another subtlety here. The universe does not observe in the human sense. There is no cosmic eye waiting for the final flash. But any observers who still existed in those remote eras would be limited by what remained visible. A civilization orbiting a late red dwarf might inherit a sky almost empty of galaxies. A culture near the end of the stellar age might experience a rare nova as something extraordinary in a cosmos that had otherwise gone quiet. And an observer living in the era of black hole evaporation, if such a thing were physically possible in any form, would inhabit a reality so alien that astronomy would mean something barely recognizable. This imagined observer is useful not as a fantasy, but as a measuring device. It reminds the mind that the final light is not just an event on a timeline. It is an event inside a transformed environment. Context gives light meaning. A supernova today occurs in a cosmos crowded with stars. A final Hawking burst would occur in a cosmos where almost every ordinary comparison had already vanished. The same amount of energy in two different eras does not mean the same thing. That is why the extreme in this question is not just a matter of lateness. It is a matter of regime. The extreme future is a place where low probability has enough time to matter, where ordinary categories lose their central role, where the background is no longer a luminous universe, but an exhausted one. Seen from there, the present starts to look almost improbably bright. There are galaxies beyond counting in the observable universe. There are active stellar nurseries, hot blue giants, supernova remnants, quasars, glowing gas clouds, planets reflecting sunlight, dust re-radiating warmth, and a relic microwave sea filling all of space. The cosmos is full of energy gradients still capable of producing order, chemistry, weather, and life. This is not the only kind of universe physics allows.
It is one stage in a sequence. The last ordinary light belongs to the end of that stage. What might that actually look like if one tried to imagine it without exaggeration? Probably not a theatrical final sunset over a final world. Probably not a single lonely star hanging in a perfect black void. Reality is usually less poetic and more precise than that. More likely, it is a category of objects rather than one cinematic scene. Perhaps the smallest red dwarfs, persisting in the remnant core of a merged galactic descendant, are among the final stars still sustaining fusion. Around them, the sky is sparse. Extragalactic structure has long slipped beyond view. Most nearby luminous peers are gone. The ambient universe is colder, older, and quieter. A surviving red dwarf there would not be remarkable for how bright it is, but for what its light still signifies. The old stellar order has not fully ended yet. Then, eventually, even those stars pass. The next, last light is no longer ordinary. It may come from a white dwarf accreting in a rare binary, a merger between compact objects, a flare from matter falling into a black hole, or some improbable remnant interaction allowed only by immense waiting time. This is not the closing of the stellar age, but the afterglow of a remnant age. Light still appears, but no longer as the universe's standard condition. Then, later still, if Hawking radiation behaves as expected, black holes begin to inherit the role of final emitters. Not all at once, the smaller ones go first. The larger ones take incomparably longer. A galaxy's central supermassive black hole, if left isolated enough, might persist until nearly everything else that could count as a major structure is already ancient beyond measure. Its evaporation would be slow at first, then hotter and faster near the end. A future with almost no luminous events left would reserve one of its last major releases for the death of an object once defined by darkness. What follows is not a dramatic ending, but a widening quiet. After the final black hole evaporates, the universe is not over. Low-energy particles remain. Space continues to expand, if dark energy endures. Radiation keeps redshifting. Time continues, perhaps indefinitely. The end of light as a meaningful cosmic category is not the end of existence. It is the end of one luminous era and the beginning of something far thinner and quieter. This is the part the mind resists, since endings are usually imagined as terminal points. But the far future of the universe is defined less by finality than by continuation without familiar structure. The last light is important not only for ending a bright age, but for revealing what lies after bright ages are no longer possible. That after is not simple emptiness. Even in the dark era, there may remain faint interactions, rare scatterings, diluted radiation fields, relic particles, perhaps even quantum fluctuations of various kinds, depending on the true structure of space-time and fields. Almost none of it resembles the classical luminous universe, but the future beyond the final light is still a physical future, governed by whatever laws remain. This is where heat death becomes useful, provided it is understood carefully. Heat death does not mean absolute zero everywhere or total absence of motion. It means a state where usable energy differences have been smoothed so thoroughly that large-scale organized processes become vanishingly difficult. A universe near heat death may still contain particles and radiation, but not the structured gradients needed for stars, planets with active climates, or rich cycles of free energy. Light can still exist in some technical sense as photons moving through space. What ends is the universe as a place where luminous structure is naturally regenerated. That resolves the apparent tension. Electromagnetism does not end, and photons do not vanish from reality. Radiation continues in different forms. What does end is the era in which light remains a common expression of cosmic activity. In that sense, the last light is both literal and more than literal. Certain processes really will produce the final major emissions. But the deeper question is not when the final photon appears. It is when the universe ceases to be a luminous place. That boundary arrives earlier than the absolute last emission. It begins when stars stop being ordinary inhabitants of the cosmos and become relics of a vanished age. It deepens when remnant-driven flares are the only interruptions to near-total darkness. The transition is layered, but its direction is unmistakable. Brightness recedes. Structure cools. Activity thins. Darkness stops being backdrop and becomes environment. One of the most striking consequences of this perspective is how it reframes rarity. In the current universe, a star is not rare. In the far future, it is. In the current universe, black hole evaporation is too faint to matter observationally. In the far future, it may become the final luminous phenomenon of real significance. In the current universe, the loss of external galaxies from view sounds impossible. In the far future, it may be the normal sky. A universe can remain governed by the same broad laws while becoming almost unrecognizable to observers within it. That is the real power of deep time. It does not just change quantities, it changes what counts as ordinary. There is a final expansion of this idea that belongs near the end of the piece, and it is less about objects than about method. Astronomy, in the age of stars, is mostly the interpretation of light. Not only visible light, of course.
Radio waves, infrared, ultraviolet, X-rays, gamma rays, neutrinos, gravitational waves, all of them extend the meaning of observation beyond the narrow human eye, but the principle is similar. The universe in its active eras announces itself through signals. It emits, it flashes, it glows, it leaves spectra, backgrounds, bursts, shadows, and redshifts. The sky is readable. This is so normal from the present vantage point that it is easy to miss how contingent it is. Astronomy is possible in its current form because the universe is still loud enough to measure. What happens when it is not? What becomes of a science built around reading radiation when radiation no longer carries a rich map of active structures? This is not merely an academic question. It goes to the heart of what it means for the luminous universe to end. The last light is not only the end of visible beauty, it is the end of easy external knowledge.
Even before the final stars, that transition begins. As external galaxies disappear beyond the horizon of practical visibility, a future observer loses the ability to map the large-scale universe directly. As the microwave background redshifts and weakens, early universe evidence becomes harder to recover. As stellar populations age and luminous events thin, the sky stops providing the same density of clues. Eventually, a late observer may inhabit a cosmos where astronomy as currently understood has become archaeology under impossible conditions. There may still be local measurements, orbits can be tracked, remnant masses can be inferred, nearby spectra can be analyzed if anything still emits strongly enough. Gravitational effects remain. But the sky ceases to present the universe as an openly legible whole. What once could be learned by looking outward across vast luminous distances may no longer be available. In a sense, the far future turns astronomy inside out.
Instead of learning the universe from abundant current emissions, observers would have to infer the universe from relics, local anomalies, and the structure of what remains. The evidence shifts from broad luminous surveys to sparse and indirect traces. A black hole's mass hints at vanished generations of stars. A white dwarf's composition hints at stellar ancestry. Orbital debris hints at old planetary systems. Heavy elements hint at long-dead supernovae. The cosmos becomes readable mainly through leftovers. That change belongs in a piece about the last light, because light is not only an object of wonder, it is the medium by which the universe becomes knowable. When the last light goes, something else goes with it, the universe's willingness to be easily interpreted from within. That is one of the deepest boundary changes of all. Before the boundary, the universe can still be surveyed through active signals. Beyond the boundary, the universe has to be reconstructed from remains.
There is a close parallel here with the shift from a stellar universe to a remnant universe. In both cases, the active present gives way to archived past. Stars become white dwarfs, neutron stars, and black holes. Radiant cosmology becomes local inference from diminishing evidence. The visible cosmos becomes a forensic one. This is not a sentimental loss, it is a structural loss. Light is one of the main ways ordered systems advertise themselves across space. Without it, complexity becomes harder to detect and harder to distinguish from emptiness. A galaxy full of cooling remnants is not literally empty, but at great enough distance and late enough time, it may behave observationally almost as though it were. That, in turn, changes the meaning of dark. Darkness in the far future is not only lack of illumination, it is lack of transparency. The universe remains real, but reality no longer shows itself as generously.
And that finally reveals why the question runs deeper than a final luminous event on a timeline. The last light marks the end of an entire relationship between the universe and observation. The bright cosmos is a cosmos that presents itself. The dark cosmos is a cosmos that retreats into inference. The universe does not only grow darker, it grows less knowable from within. Even the most powerful future observer could not simply command the sky to speak if the sky no longer emits in rich ways. Knowledge itself becomes more local, more partial, more historical. The universe grows older, not just in content, but in accessibility. This gives the final black hole era an even stranger role. Hawking radiation, if it defines the last major light, would be not only the terminal release of energy from the longest-lived macroscopic objects, it would also be one of the final instances in which the universe still says anything noticeable at all through radiation.
The death of a black hole would be a physical event and a final act of disclosure. After that, the cosmos would persist, but increasingly as something no longer broadcasting itself. That is a powerful way to widen the ending. The dark era is not merely an era after stars, it is an era after easy astronomy. The universe can continue forever and still, in a practical sense, become harder and harder to know. Facts survive their evidence. That may be the most subtle tragedy in the whole far future. Not destruction, withdrawal. The sky today is generous. It lets structure be seen. It lets distance be measured. It lets history arrive in photons. It fills detectors with clues. It offers a cosmos that still produces enough difference, enough heat, enough light, enough contrast to be read. The future removes that generosity one layer at a time. First, the universe becomes harder to see in full. Then it becomes harder to see in part. Then it becomes hard to see at all. And still it goes on. That continuation, even after light has ceased to make the universe legible in the old way, is part of what makes the far future so unsettling. The final light is not just the close of brightness, it is the close of openness. Beyond it lies a future that does not announce itself clearly, a reality still present, but no longer eager to be observed. That is why the current age is so exceptional, not only because stars shine, because the universe is still readable. That brings the question back one last time, directly and cleanly. What is the last light the universe will ever see? If by last light one means the final familiar starlight, the answer most likely points to the last surviving low-mass stars, probably red dwarfs or late-formed merger products, able to sustain fusion after almost every brighter star has died.
They mark the closing edge of the ordinary stellar universe.
If by last light one means the final, significant luminous events after stars are gone, the answer shifts to rare remnant processes, accretion flares, compact object collisions, delayed explosions from degenerate remnants, or other sparse releases in a remnant-dominated cosmos. If by last light one means the final major electromagnetic emission expected under current physics, the best candidate is the Hawking radiation from the last evaporating black holes, especially the most massive ones, whose lifetimes extend furthest into the future. In that broadest sense, the universe's final light may come from the death of its darkest objects. And if unknown physics intervenes, proton decay, vacuum instability, altered dark energy, hidden particles, departures from semi-classical gravity, then the details could change, though not the larger truth that the luminous universe is temporary. That answer is not a loophole. It is the honest shape of the problem. The farther ahead the universe is followed, the more last light becomes a set of nested endings rather than a single switch. There is the last age when starlight is common. There is the last visible sky in the old sense. There is the last rare flare from dead matter. And beyond all of them lies a future that continues without needing brightness at all. This is why the final light is so hard to picture. The human mind was built inside the luminous interval. It expects the visible to be normal. It treats stars as part of the furniture of reality. But stars are an event. Galaxies full of active light are an event. Even a cosmos rich enough to host questions about its own fading is an event. The future strips that assumption away. 1 trillion years from now, the universe may still contain small stars, but the wider cosmic scene will already be diminished.
A quadrillion years from now, the ordinary stellar age may be closing or gone. Much farther still, dead remnants and black holes dominate. Far beyond that, even black holes release what they have left and disappear. Then the dark era opens wider and wider, not like a curtain falling, but like a horizon receding forever. That widening future is the real ending, if ending is the right word. Not a collapse into nothing, not a final frame. A transition into a reality where the old luminous patterns no longer organize the whole. And that is perhaps the strangest part of all. The last light does not merely tell the universe that something has finished. It reveals what kind of place the universe was all along. Not a permanently shining cosmos, not a machine designed to stay visible. A thermodynamic unfolding, with an early darkness, a long bright middle, and a later darkness of another kind. The stars are real.
Their beauty is real. Their abundance is real. Their permanence is not. Every bright object now stands inside that truth. The sun, steady over Earth, belongs to a temporary order. The Milky Way, enormous and ancient, belongs to a temporary order. The great galactic webs seen by powerful telescopes belong to a temporary order. Even the smallest red dwarfs, those patient keepers of the far future, belong to an order that also ends. When that order is gone, the universe does not become meaningless. It becomes harder to narrate in familiar terms. A dark era is still an era. A remnant cosmos is still a cosmos. A particle-thin future is still real. The loss is not existence. The loss is luminous familiarity. There is one final image worth keeping, though not as literal prediction, more as orientation. Imagine a bright night under a young sky. Countless stars, unresolved bands of light, structure in every direction. Now remove the nearest layers first.
Galaxies beyond the local region fade from view with expansion. The local galaxies merge and age. Star formation withers. Bright blue stars vanish early. Sun-like stars follow. Red dwarfs remain, small and stubborn. Then even they are gone. Remnants cool. Rare encounters puncture the dark. Black holes inherit duration. Eventually, one of the largest, after a span that makes every earlier age look immediate, releases its final radiation and is no more. What remains form of persistence. The last ordinary light comes from the last stars. The last unusual light comes from the universe's dead and dying remnants. The last great physical light may come from black holes themselves. After that, the universe keeps going.
And that may be the most unsettling conclusion of all. The final light is not the closing act of everything. It is the point after which the universe no longer needs illumination to continue being real. The bright age passes, the dark age opens. Time does not stop to mark the transition. Space does not fold itself shut. The cosmos simply becomes harder and harder to set on fire. Seen that way, the night sky now is not just beautiful, it is historically located. It belongs to a rare interval when the universe is still openly radiant. Every star is evidence that the long descent has not yet gone very far. Every galaxy is proof that distance still carries visible meaning. Every sunrise is a local expression of a much larger condition. The universe is still in its luminous era. One day, unimaginably far from now, that statement will no longer be true. Not suddenly, not everywhere in the same sense, but truly.
And when the final light is finally gone, whether counted as the last star, the last flare from dead matter, or the last black hole radiation, the future does not close behind it. It widens ahead into silence, into dilution, into the cold persistence of whatever remains when brightness has become a memory written only into the structure of time. That farther dark is not empty of physics, it is empty of the old kind of sky. And from here, beneath a universe still full of stars, that may be the clearest way to understand what the last light really is, not just the final glow, but the last sign that the cosmos is still a luminous place. When that sign disappears, the universe crosses a threshold from which there is no return to ordinary radiance. Not a ruin, not an apocalypse in the cinematic sense, but a state change at the largest scale, the kind of change only deep time can produce.
The kind that makes the whole age of stars look like a temporary clearing in a much longer night. The sky above the present world feels timeless. It is not timeless. It is early enough. And somewhere beyond numbers that language can barely hold, beyond the last red dwarfs, beyond the final collisions of remnants, beyond the delayed whisper of evaporating black holes, the universe continues into a darkness no human eye was built to imagine. Still real, still unfolding, still carrying the aftermath of light, long after the age of light is over. If there is a final comfort in that, it is not that the stars last forever. They do not. It is that the universe remains larger
than any one phase of itself. Brightness comes, brightness goes, structure appears, changes, thins, and yields to colder forms. The end of the luminous cosmos is not the end of reality. It is the opening of a more distant and more silent state.
And that future is already waiting inside the stars now visible tonight. Near the beginning, the question was where the boundary lies. The deepest answer is that the boundary is not a line drawn on a calendar. It is the slow crossing from a universe where light is normal to one where light is rare, and then from rarity to near absence. The crossing begins already in the decline of star formation. It deepens in the survival of only the longest-lived stars. It becomes unmistakable when the stellar era closes. It reaches its most extreme form when even black holes have surrendered their stored future. Then only the farther dark remains. Not empty, not over, just beyond the last light. And for a universe that now seems full beyond measure, that is the most astonishing truth of all.
If this glimpse of the universe's final light stayed with you, subscribe. The cosmos does not end all at once. It fades, layer by layer, until even brightness becomes rare. And if that future is still on your mind, leave a comment below. What do you think would be the strangest thing about living in a universe after the stars are gone?